Welcome to AVR Coding 101, Lesson 2. This lesson will focus on timers. Specifically, we'll be using the TCB0 timer to create a repeating interval, and we'll be coding an interrupt service routine. Finally, we'll be using that information to be able to blink our LED that we had in Lesson 1. So the AT-Tiny1616 has two general purpose and three special application timers. The two general purpose timers are the ones that we'll be using in Lesson 2, 3, and 4. Typical microcontroller timers are either 8-bit or 16-bit, though there are some cases where there is actually a 12-bit timer, but let's focus on 8-bit and 16-bit timers. An 8-bit timer has only 8 bits, that means its maximum value is 256, and a 16-bit timer has 16 bits, so its maximum value is 65,535. If our clock is running at 20 megahertz, we can do the math there, and we end up with 3.3 milliseconds as the maximum duration that we would be able to measure with our timer. That's not a very big amount of time, and so some timers, not all, include the capability of a prescaler or a divider. If you had a prescaler of 1024, then our 3.3 milliseconds now becomes 3.38 seconds. Not all timers have prescalers. If a timer is executing code, then you could have a small piece of code that actually does a counter within that and execute its significant code every n times. And so in essence, you've implemented a prescaler, but you've done it in code as opposed to hardware. The timers on the AVR series have a couple of different functions. They can, as I've mentioned, execute code. They can also control an I/O pin. When it's executing code, it's called an interrupt service routine, or ISR. The microcontroller is capable of multiple different interrupt service routines. There's a table defining the address of each of these service routines. For timers, the interrupt service routine occurs at a given interval that we specify. This interval is dependent on the value we give it and the speed of the CPU that we're running. The AT-Tiny1616 has multiple clock references. We're using the 20 megahertz internal oscillator. There's also an ultra-low power oscillator running at 32 kilohertz. If you were to use this oscillator, then the duration or the amount of time you'd be able to measure is significantly larger. Simplest way to think about a timer is it has a mode, which it's going to be doing. It has an interval, how often it's going to be doing, and then it has an action or actions. What is it going to be doing? So we put this together, we end up with perform an action at a specified interval forever. And that is the use case that we'll be using in Lesson 2. We mentioned there's two general purpose timers on the AT-Tiny1616. They're TCA0 and TCB0. There's also a couple other timers that are special use. We're not going to be getting into those in this lesson. Both TCA and TCB are 16-bit timers. TCA supports a wide range of prescalers. TCB0 only supports 2. Since we need a large range of prescalers in another upcoming lesson, for this we're going to use TCB0. We want to configure TCB0 for a reoccurring event. This is called a periodic interrupt mode, and we'll be writing an interrupt service routine to occur on a given interval. A lot of this covered in detail within the datasheet. You're welcome to read all of that, but we're going to stick with a relatively simple use case where we're going to configure our timer TCB0 to emit an event on a period, and then we're going to execute a small piece of code every time that event occurs. Let's assume we want to turn our LED on and off using a timer instead of the button that we used in Lesson 1. And let's say we want that interval to be 1 second. If our CPU is running at 20 million cycles per second, or 20 megahertz, if we wanted an interval every 1 second, we would actually have our timer count up to 20 million. For we know that it's a 16-bit timer, and that's limited to 65,535, so we need to do something. If we had a wide range of prescalers, we could divide down our clock to count up to the equivalent of 20 million. However, we don't in the case of TCB0. Instead, we will count up to only 1 millisecond, and then every 1,000 instances, or every 1,000 events, will then toggle our LED. This actually has a convenient side effect. We now will have at our disposal a 1 millisecond timer we can use for anything we want. All we have to do is maintain a global variable that we increment within our timer. So now we look at it. 20 million is our CPU frequency. We want to have it occur 1,000 times per second, so now we only have to count up to 20,000, which is less than our 65,535, so we're good. The mode we want to use is we want to capture an event as we reach that 20,000 mark. So we're going to count up from 0. When we reach 20,000, we want to capture an event, perform some action, and then start over again. From lesson 1, we talked about memory locations within the CPU for our I/O registers. There's also memory locations for our timers. TCB0 starts at the address of 0A40 hex, and at that location is the following data. We have a control A and B. We have some reserve space we're not allowed to touch. We have event controls, interrupt controls. We also have some counters and some compare register information. And those are the ones we're going to be using for this example. The first thing we need to do is we need to determine what our interval is going to be. We said we want to have it occur 1,000 times per second. So we take our CPU, we divide it by 1,000, and we end up with what our interval is going to be. The interval counter starts at 0, so we don't actually want to count to our interval. We want to count to our interval minus 1. Since the first tick is actually at 0, our second tick is at 1, etc. So we set our compare register to our interval minus 1. The next step is we want to perform a task. We want to enable the interrupt mode, so we'll be able to write an interrupt service routine. So now we have our interval set, and we have the type of operation we want to take. The last step is we need to enable the interrupt service routine, and then we need to enable the timer. Now we need to write our interrupt code, our interrupt service routine. Every interrupt service routine within the microcontroller has location, and it's called a vector. We will be working with TCB0, its interrupt vector, and we allow the compiler to know what we're doing by using the ISR syntax. So here we have ISR of TCB0 int vector. That's going to be our interrupt service routine. Here it is, it's doing nothing, but now let's start putting some code into it. One thing we have to do within our interrupt service routine is make sure we re-enable it just before we exit so that it can be called again later. We said we wanted to have a global variable to keep track of our 1 millisecond timer. So here we've set it up. We have timer counter, and every time our interrupt occurs, we simply increment it. And then we reset the flag for our interrupt so that it can occur again later on. We've declared our interrupt counter as an unsigned 32-bit int. Timer underscore counter is a global variable. We could use it anywhere within our code, but it's good practice to actually put a little function around it and using the function rather than directly accessing our variable. So here we've created a milliseconds function, and all it does is it gets the timer counter. And we may want to have a delay function at some point, and so we've just coded one up here as an example. All it does is it grabs the current milliseconds, adds to it some delay that we want to perform, and then it waits until the millisecond timer exceeds whatever that computed value is. There is one thing wrong with our milliseconds function that we have here, the one that says return timer underscore counter. It's referencing that variable, and it is possible at the very same time that we're referencing it, the interrupt occurs and causes the value to change while we're trying to read it. This would result in an unpredictable value. So what we want to do is we want to temporarily block our interrupts from occurring while we go and read that value. The method we use to prevent our code from being interrupted is referred to as an atomic block. The AVR header files provide us macros that handle this for us. What we want to do is we want to create an atomic block while we're reading our timer counter just for that brief moment, and then we want to restore the state of the interrupts. So instead of returning the milliseconds value timer counter directly, what we do is we temporarily copy it to a local variable, doing that within an atomic block so it can't be interrupted, and then we can return that value. If we didn't do this, then theoretically each time we called milliseconds, we may or may not get the actual value. We may get some truncated portion of it. Okay, so we now have a timer, we have an interrupt service routine, and we have a global counter. Let's control our LED. Our timer is occurring once every millisecond or 1,000 times per second. We want to update our LED only once per second. That would be every 1,000 times that our interrupt has occurred. We have a function that we can call called milliseconds. What we want to do is we want to compare our milliseconds. You can do this a couple of different ways. For code that's running very quickly, it's easy to use a function called modulo. It's a mathematical operation that simply divides A by B and gives us the remainder. If the remainder is 0, then we know that A is perfectly divisible by B. So if we were to do milliseconds modulo 1,000, that value would be 0 every time that the milliseconds was a multiple of 1,000 or perfectly divisible by 1,000. If you were running a lot of code, then it's theoretically possible that our milliseconds counter might go 999, and then by the time we come back and check it again, it's at 1001, because more than 1 millisecond of code had been executed. In that case, you would want to create a variable which is equal to milliseconds, add to that the amount of time you want to have pass, and then check for that value. And that's exactly what we did in that delay function. So now let's put all of that together with the code that we have from lesson 1 and the timer that we've just done, and let's blink our LED. Here's our LED code from lesson 1. We have the ability to set up an LED, we can turn it on, we can turn it off, and we can toggle it. We don't need our button code this time around, so let's skip over our button code. And here is our timer code. So we're keeping a global counter, timer counter. We've computed our interval. Inside our interrupt service routine, we increment our counter, and then we want to make sure that we clear the interrupt flag. We want to set up this timer. We set the compare to our interval. We then enable our interrupt service routine, and then we enable our actual timer. And then we want to make sure we enable interrupt, and then we're good to go. Inside our little millisecond routine, we're using the atomic block so that when we read the timer counter, we don't get interrupted and we don't get a corrupted value. Here's our main. We set up our milliseconds timer. We set up our LED, and then we grab the current time or the current milliseconds with our local variable. And then inside our while loop, we say if our local counter is less than the milliseconds, then we want to toggle our LED, and then we want to move our counter into the future by 1,000 milliseconds, and then we continue through our loop. Every 1,000 milliseconds, the LED will get toggled. So let's go ahead and build this code. And let's go ahead and upload it. There we go, it's uploaded. That doesn't look like every millisecond. What's wrong here? Let's take a look. Indeed, our LED is not blinking every millisecond. It seems to be much, much slower than that. Why is that? Our timer we've set is at 20 megahertz, and we've said we want our millisecond timer every 1,000. You'll notice in the code that I showed momentarily that we set a pin, and this is following along with what we did in lesson 1. So we're setting a pin as output, and then within our interrupt service routine, we're simply toggling that pin. If we look at these two images, we can actually look at the live oscilloscope for just a moment here. So there we go. So in this case, we can see that the distance between those two vertical lines is actually 6 milliseconds, not 1. So we're 1/6 as fast as we thought we were. So there's a clue right there. Our clock is 1/6 as fast as we thought it should be. Let's take a look at the data sheet and see if we can find a clue. Section 10 talks about clocks. Section 10.3 talks about the main clock, the one that we're using here. The clock can have a prescaler. That's interesting. A prescaler would divide the speed of our clock. Let's do a little bit more digging. Main clock after reset, every time we've powered on our AC1, the prescaler has a division factor of 6. Well, that's exactly what we're seeing. Our clock is 1/6 as fast as it should be. The clock has a register for controlling its prescaler. So the main clock has a register controlling its prescaler. We don't really want to change the prescaler to some other value. We just simply want to disable the prescaler, and sure enough, there is a prescaler enable bit. So when it's 1, the prescaler is available, and when it's 0, the prescaler is disabled. We want to disable the prescaler, so we need to set that bit to 0. So we want to disable the prescaler. And there is a bit for disabling the prescaler. We simply need to mask out the control to clear that prescaler. If you were to do this, it would have no effect. It turns out we're not able to clear that bit. It's protected by a configuration change protection field, but we can unlock that protection momentarily so that we can make the change. We're going to do the unlock and then immediately make the change to that code in our example. So that's this little secret sauce section right here. We unlock the protection and we immediately set the prescaler enable bit to clear it. So now what we want to do is down inside our main, we want to call our new piece of code here. So that's the very first thing we want to do. Then we can set up our milliseconds timer and we can set up our LED. Let's build and upload our code. And now if we go and look at the oscilloscope, let's see where we're at here now. We adjust our cursor. And we can see, sure enough, we're now at 1 millisecond. And if we look at our LED, 1 second on, 1 second off. 1 second on, 1 second off. So there's our finished code. To recap, for lesson 2, we established a timer. We wrote an interrupt service routine for that timer. The interrupt service routine was triggered once every millisecond. We maintained a counter, and then we used that counter to then update our LED every 1,000 times that it changed, or every 1 second. And now we have our LED blinking at intervals of on and off 1 second each. That concludes lesson 2.